Okay, we're going to start part 3 of week 4 by doing a series of problems taking into account tension in various situations. Now here we have a person standing on a tightrope, and it causes the tightrope to sag by 5 degrees. The system of interest here is the point on the wire where the tightrope walker is standing. If he weighs 50 kilograms, what is the tension in each wire? Now in this case, we can draw our free body diagram this way. Here's his weight, tension on the right and tension on the left. Now because these two angles are the same, the tension in each of these lines is going to be the same. So if we find out the tension in one, we will find out the tension in the other. Now let's start working on this problem. First of all, we know that we can divide both TR and TL into TRX component and TRY component. And we can also divide TL into the TLX and TLY components. Now the reason that's important is, remember, the person's not moving, so the sum of the X components, TLX or TRX and TLX, has to equal 0. Otherwise he would be moving from right to left or left to right. So that TRX has to equal TLX. The other truth is that the Y components, TLY plus TRY, have to counterbalance his weight. Now his weight is 70 kilos times 9.8, which is 686 newtons. And TLY, now if we look at the Y here, the Y is going to be on the side opposite the angle, so TLY is equal to TL sine 5 degrees. And the same is true for TRY. It's TR sine 5 degrees. So we know that 2 times, because these two are equal in this situation, 2 times TLY is equal to 686. That is 2 times. We know that this quantity TLY plus TRY is equal to W. We also know these two are equal to each other, so we can say that 2 times TLY is equal to 686, or 2 times TL sine 5 degrees is equal to 686. And we can use that to calculate TL, and TL comes out to be 3,930 newtons, and that's actually what TR is going to be as well, 3,930 newtons. So now let's look at our next problem. And here we have a guy that looks like Tarzan. Tarzan is going to be pulling on this line, and if you have if you're looking at the strategy for how to do a problem with Tarzan, the first thing is to sketch the problem. Now, this is a very complicated sketch. I can tell you right now, when I do my problem sketches, they are more like stickmen. The second thing is you identify the forces involved. The tension force, which is shown here, and the weight force shown here. You also then, once you've identified the forces and used an arrow to indicate each force that's involved, you make sure that you define the system in a proper manner by drawing a circle around the system that's important. Now, if there's any force that's not within the system, then that's not considered. And in this case, the force is not in the system of interest since it's exerted on the outside world. And that's this right here. And your free body diagram looks like this. The tension up exerted by the rope or vine is equal to the weight down. And then lastly, you make a equation of sorts to show the relationship between the forces in the free body diagram. And if Tarzan's not moving, then the tension has to equal the negative aspect of the weight. Now, if he's moving, everything changes. So let's take a look at another problem. In this case, we have two barges, or we have two tugboats that are pushing a barge. This one is exerting this much force. This one is exerting this much force. The resultant is an acceleration in this direction with this angle. And what we want to know is there's going to be a drag force that's working against this. Here's the free body diagram. The system in question looks like this. And here's the two forces of the two tugboats and the net force of these two tugboats. And the drag force acts against that. So if we know that the mass of the barge is this, and the acceleration of the barge, based on the mass and acceleration, we can calculate what F net is. And if we know that F net comes from these two forces, we can find out what the drag force is. So let's take a look at how to do this problem. So we start out, we have this barge, and I'm going to go ahead and draw the forces that are acting on the barge. And we know that MA is equal to the F net that causes the barge to move, and we know that M is 5 times 10 to the 6th kilograms, and that A is 7.5 meters per second squared. Oh, times 10 to the minus 2, excuse me. And so if you multiply that together, we get F net is 3.8 times 10 to the minus or plus 5 newtons. So that's the F net, and F net equals F, which is results from these two barges, or these two tugboats, minus the drag. So if we can calculate this, then we know this, we've just calculated that, then we can find this. Now, because fortunately these are at right angles, this is the hypotenuse of a right triangle, therefore F squared is going to equal Fx squared plus Fy squared, or F equals the square root of fx squared plus fy squared. And fx squared is right here, 2.7 times 10 to the 5th. And y is 3.6 times 10 to the 5th. And the square root of that. And the answer here, when you do all the math, is 4.5 times 10 to the 5th newtons. So the applied force, or F, is this number right here. So if we take F net and we rearrange this, we know that F net plus FD is equal to F, and therefore FD is equal to F, which is 4.5 times 10 to the 5th minus 3.8 times 10 to the 5th, and we get D is 7.0 times 10 to the 4th newtons. And so that's the drag force that is now operating. Now here's another problem that we can work on. We now have a traffic light that weighs 15 kilos, and the question is, what is the tension on each wire? So you do the sketch, you show the forces. Here's tension on one and tension on the other, the angles involved, the weight, and then we do a free body diagram, which is right here and here. And we divide this up into the y components and the x components. We know that the y components are going to equal the weight, and the x components have to cancel each other out, otherwise the situation would move. The traffic light would move. So let's go ahead and take a look at this calculation. First of all, we know that TLX has to equal TRX. And we know that the x component on both of these is the cosine of each one. So if they have TL, that's T1, and that's going to be the cosine of 30 degrees, has to equal T2 cosine of 45 degrees. And if you work this out, it's going to be T1 times 0.866 equals T2 times 0.707. And if you rearrange this, you ultimately can make T2 equal 1.225 T1. Okay? Now we also know that T1y plus T2y has to equal a minus W, which is, and minus W, if it's 15 kilos, it's 147 newtons, or 15 times 9.8. So we can put this in. Now it's going to be T1 sine 30 plus T2 sine 45 equals 147, and T1 and the sine of 30 is 0.5, and the sine of 45 is 0.707. And at this point, we can use this identity right here and substitute this for T2. So that's going to be T1 times 0.5 plus 1.225 T1 times 0.707, and if you do the math here, you end up with T1, equals 108 newtons. And if you substitute this in here, then T2 is going to equal 132 newtons. So that's how you do this problem right here. And we're going to stop at this point, and when I come back, we'll finish up